All right, good morning. Let's get started, okay? So I need to finish a couple small things from previous lecture, and then we'll get on to the new topic called first order differential equation. And the first type of first order differential, which is the linear equation. Okay, so in previous lecture we have talked about the definitions of differential equation, ordinary differential equation, okay, and partial differential equation. So there's different levels of definition in here, right? And in particular, we also talked about what we will deal with in this class, linear ODE. Okay. So linear ODE is what we will deal with in this class. And linear ODE always takes the following format. And you have let's say if you have a unknown variable that is function of t, then you can always form a differential equation with this format. So as long as you see a differential equation that actually conforms with this format at here, then you can conclude that you're dealing with is a linear ordinary differential equation. Okay? Yeah. So these coefficients at here, okay, for each one of the term. So first of all, you can see, alpha n to alpha naught. They're a function of t. They're not a function of this unknown function y. Okay, so they're not function. They're not a function of y. That's very important. Okay, because if they are a function of y, then this is not a linear ODE basically. Okay. But they can be function of t, and that is fine. And second of all, okay, we always try to understand things from input-output point of view. So in this case, f of t is called input. So you have input into the system, input force or input current, input voltage. It doesn't matter what it is. And then y of t is the output. So this is very important. Always remember which one is input, which one is output. And the objective, right? The objective is basically to get a solution. So to get a solution out of this linear ODE or ODE. Okay? That's objective. And then we will basically show you for first order system, how do we get a solution? For second order system, how do we get a solution? Things like that. And another thing that you will see later, okay? So I said f of t is input, then f of t, okay, could be 0. So you can have a 0 input to the system. When you have a 0 input to the system, okay, then this equation becomes an equation called homogeneous equation. Okay. Now you might wonder, well, okay, so if input is 0, then what is going on? So is there what? Then why do we still bother to solve the system, right? Yeah. Now the difference is, okay, when you have a system described by a differential equation, the system output y is not only driven by external input f, it can also be driven by so-called initial value. Okay? So let's say if you have a RC circuit, even if you don't have any voltage input, but if initially the capacitor has certain voltage across it, right, then there's still going to be certain action going on within the circuits, okay, until it's settled down. So you can have a non-external input to the system, and that kind of system is called homogeneous equation. Okay? Yeah. And of course, if f of t is not 0, then it's called a non-homogeneous. Okay. So those are the two different scenarios that we will deal with. Okay. Yeah. Now we have given you a few examples in the previous lecture. So for example, you have mx double dot plus bx dot plus plus kx equal to f of t. Okay, this kind of example. In this kind of example, your m, b, k, okay, we consider them, if we consider them as a constant, if they're constant variable, constant not variable, constant numbers, okay, like this, and we call this kind of system time invariant system. In particular, this has become a linear time invariant system because this is a linear ODE, right? And I will actually quickly prove why it's a linear after this. So this will be basically the system is time invariant. Because the system parameter do not change, and they're being kept as constant, and that's why the system is actually becoming time invariant system. However, okay, if m of t, b of t, k of t, okay, very much like the general format, right? You use a function of t to represent the coefficient here. As a matter of fact, the coefficient is a function of the system parameters. Okay, so if these are not constant, then we're going to deal with is a time varying system. Okay, so just bear in mind of the difference set here. Okay. So when you have a linear ODE, those are the type of variations that we will see. Okay, so now let me give you a quick demonstration or illustration why we call it a linear ODE, right? So I'll use use an example, first order example to illustrate. Let's say I have a system dy over dt and plus, let's see, using the symbols like this, alpha y equal to this. Okay? Yeah. So let's say this is a system, this is the first order system, right? Yeah. And according to the notation, we call this a linear ODE. Okay? And we'll try to show you why this is actually linear. To show you why is basically we'll try to show the system satisfy the superposition property. Okay. So satisfy superposition property essentially means if you have input C1, Y1, C2, Y2, it should, sorry, this is not input. If you have a C1, F1, C2, F2, it should produce C1, Y1 plus C2, Y2, right? Okay. So let's try this. Suppose F1 produce Y1 and F2 produce Y2. So what does that mean? Basically means you have dy1 over dt plus alpha naught y1 equal to F1. Right, so when your input is F1, you have output Y1. When your input is F2, your output is Y2. Right, so this is essentially what this means. Now in this case, we don't have a solution yet, right? But you know you can get a solution, but you do know that input F1 produce Y1, input F2 will produce Y2. Okay? Yeah. So let's call this is equation 1, this is equation number 2. Okay. And then I'm going to multiply equation 1 with C1 and multiply equation 2 with C2. And then we'll add these two equations together. Okay. So multiply equation 1 with C1 on both sides. Multiply equation 2 with C2, of course, on both sides. And then you add left, and right. Okay? So if you do this, so what we're going to get, right? So C1, C2 here, and then you add these two together. What do you get? You get d over dt inside is C1, Y1, C2, Y2 here, right? Yeah. And over here you have alpha naught t, that's a common term. Inside is C1, Y1, C2, Y2. Okay. And on the left side, on the right side here, you have C1, F1, and C2, F2. Okay. So if you add these two together, you get this. So essentially you get another differential equation. And for this differential equation, your input is this. Your output is this. Right? So in this differential equation, you can see input C1, F1, C2, F2 produce the output C1, Y1, C2, Y2. And that's exactly what we're trying to prove, right? The superposition property. So you basically can conclude that this first order differential equation is a linear ODE, or actually represents a linear system. Okay? Yeah. And you can expand this to a second order, easily second order, or much more higher order ODEs, okay, systems. Okay? Okay. So let me summarize a little bit, and then we'll carry on here. Okay? To summarize, we have different definitions, and this is essentially the order, the tree. A different hierarchy in terms of differential equations. The top level is differential equation. Okay? That includes all the possible scenarios. And then you can branch out. And one branch, you can see it is a partial differential equation. And the other branch will be simpler ones. And that will be the ordinary differential equation. So to jog your mind, partial differential equation are equation deal with function of what? Multivariable functions, right? And ordinary differential equation are equation deal with only a function of a single variable functions and its derivatives. Okay. From ODE, okay, and then you can have a linear ODE. which we just talked about. And of course, you can have nonlinear ODE. So if it's not linear ODE, then it's nonlinear ODE. If it's not linear ODE, then it's nonlinear. And from the linear ODE, you can have a time invariant. So altogether, you get LTI, right? So this branch will give you an LTI, and this other branch is time invariant, and that's another branch. Okay, so typically, as I said, we typically will deal with this, okay? And sometimes we are also here. Okay? For some examples, we probably will see this, but most of the time should be this portion here. Okay. Is that good? Yeah. So that's the bigger picture in terms of what differential equations are and what we deal with in this class. So let's now dive into the details. Okay. Most of the time we're going to spend for the rest of the term will be how to solve differential equation, and given system of its different signal, how do we get the dynamics out of the system, which is described by the differential equation. Okay. So first that we're going to look at is first order differential equation, and we'll look at particularly the linear type. Now, as you can see, I didn't put the ordinary here. So I didn't put the linear first order ordinary differential equation because, as you some example, you will see they are not ordinary. They can be basically a nonlinear type. Okay, yeah. Okay, so let's take a look at what we're going to deal with. Okay, general format. So general form of a differential equation, first order. Okay. You can have the following general formats. So consider y equal to y of x. So consider y is a function of x here. So x is the independent variable, just like we used t, right, previously. Okay. Then you can have the following two general formats. So y prime equal to a function of x, y. Okay. So y prime dy over dx. That's first order. And equal to certain combination of x and y putting together, and we call that function f. And this one, we call this is explicit. Okay, so explicitly you have the expression for this dy over dx. Now sometimes you can also have a format like this. So everything is mixed together. Okay, so x, y, y prime, they are mixed together, equal to 0. So you don't have explicitly the expression for y prime. This one here, we call that implicit. Implicit. Most of the time will be the explicit. Okay. Yeah. So we'll look at a few different today, right? We'll look at the linear one here. We'll look at the linear differential equation, first order particular. So the format of linear first order, let's just write on first order. Okay. Linear first order differential equation will take the following format. you have a coefficient, okay, for y prime, and you also have a coefficient for y, and then equal to a function f, which is input. Okay, yeah. And this is the linear format, which is essentially the linear ODE that we just presented, right? Okay. Now for this one here, we can always actually rewrite this, okay, which what we call a standard format. So you can always rewrite it by dividing a naught x for both sides. So if you divide this a naught and you can normalize the coefficient for y prime to be 1. So then the coefficient for y prime becomes 1, right? So then this time you can get a y prime with a coefficient of 1, and then plus a1 over a naught. So I don't know what they are, but once you divide it, and you probably will get another function, let's call it p of x, okay, and times y. And this side here, okay, let's call it q of x. So you can always rewrite any first order like this by turning it what we call a standard format. Okay. Okay. So a lot of time I will do this step first and turn it into a standard, and then we apply the technique to get a solution. Okay. Okay. So let's focus on this first, and then we have a different other form of first order. Right. This time we're talking about linear first order differential equation. Yes.
So then you just combine these kind of equations by the high order.
Yes. Yeah. I mean, in this case, it's first order, right? Yeah. Okay. So let's look at different ways of solving linear first order differential equation. Okay. Again, we're going to have to look at two different scenarios at here. The first scenario, I think I mentioned this just moments ago, is that this input, right? This input at here can be 0. So basically, that's the term we call it homogeneous, right? So this term can be 0, and this term can be non-zero, of course. So we look at the first case. Is homogeneous case. Let's look at how to solve a homogeneous one, so that using the standard format, okay, we get this one, right? So that's when the equation becomes homogeneous. F of x equal to 0. Okay. For this one, it's actually very easy to solve. I believe, I don't know if you, sometimes they actually teach you at the end of the first year calculus number 2, calculus 2. We use a technique called separating variable technique. Okay, we use a separating variable technique to solve this. So here's what we do. Y prime is dy over dx. And then we're going to move the px times y to the right side. So that's px times y. So it becomes a negative. Okay. And then we look for terms associated with x and also term associated with the y. So you separate these two variables out. So for now, you can see you have y dy like this, right? And then you have your px and dx like that. So you put all the like-minded together. Okay, so x and y, okay, put in two groups. And once you're done with this, and you can literally see dy on one side and dx on the other side. So now we can integrate both sides. Okay, and integrate both sides. Integrating both sides means you basically just add an integration sign. Okay. If you add an integration sign, you get integrating dy over y equal to negative this function and dx. Okay. The left side, that's easy, right? It's 1 over y dy. So the results of this integration should be, what should that be? Ln y. But it has to be positive, right? So we put an absolute sign around the y. And this side here, I don't know what it is, because if we have a given question, then we will have the p of x. But for now, we will leave this p of x as it is. Okay. However, you actually don't stop at it here. So when you integrate this term, so there's no limits at it here. So technically, the results of this term should be what? Ln y and then plus a c, right? Yeah. Now, but I don't want to have the c on the left side. So I want the c to be on the right side. So I'm going to just basically move the c to the other side. I might as well put the negative sign on the outside here. But c is a constant, so when you move around, you don't have to carry the negative sign. So you can just move the c to the other side and still call it c, and which is fine. Okay, yeah. So this is the results. Now remember, we're trying to get a solution for y, right? So that's not a solution for y yet. So we need to do one more step. How do I get rid of the ln sign? So what do? We take exponential on both sides of this equation. Okay. So taking exponential of both sides of the equation, then you get absolute y at here, and this side here you get e to the power of negative px dx. Okay, so this is a e to the power of one term plus another term. So I can write it e to the power c. Right? So e to the power of a plus b equal to e to the power a times e to the power b. And e to the power of c is a constant, right? So I'm going to call this as just a constant, call it a here. Okay. So absolute y equal to a constant times e to the power of this term. How do I get rid of the absolute sign? So y, if y has absolute sign around it equal to something, then the y could be positive, negative, and a times this. Now this is a solution. Okay. However, this is the solution. We can simplify it to one more step. Because you have a positive and negative a at here, which is a constant, and that constant right now we don't know. If you have initial conditions, we'll be able to calculate the constant a, right? So the actual value for the a at here, okay, has to be determined. So this one here, so this term, okay, that depends on the so-called initial condition value. Okay, initial condition value. So in other words, I don't really have to carry this positive and negative sign all the time. You could just call this positive and negative a as Call it the B. Okay. Yes.
I don't think A can be positive or negative because A equals to e to the power of c. How do you get like a negative value?
Why not? I mean, this term has to be positive, right?
Yeah, no, but like I mean A will always be positive.
No. If I have an absolute value y equals, let's say, 3 times this, times this, for example, what could be the y solution? Y is, can y be this? Can y be that, right? So when you put a negative sign, put an absolute sign around it, you get this. So mathematically, you need a positive and negative sign in front of A here. That makes sense? But, just as I said, the A is a constant, right? What is the value of the constant? We don't know. That depends on the initial value. Okay? So at the end of the day, you actually you won't have both the positive and negative here. You will have only one, and that's for sure. Yeah. Okay. We'll see in examples. It probably will be clear. Okay. Okay. So basically, now for this homogeneous case, here's your general solution for y. Okay. The b at here, if there's no initial condition, then we cannot calculate the b value. So let's look at an example here. Okay. So let's say I have a first order differential equation, y equal to, I'll put a negative here, y equal to negative 2xy. And x can be negative infinite to positive infinite. So now let's try to solve this equation in here. Okay, let's try to solve. To solve this equation, we use separating variable technique. Okay. So dy, y prime is dy over dx. So you move all the y together, you move all the x together, you get this. And then you take integration of both sides, and you get ln y equal to negative 2x dx, okay, and plus c. Okay. And this term here is negative x squared plus c. Okay. And that's your ln y. Then the y can be written as b times e to the power of negative x squared. And b can be either positive or negative. Okay. So this is your general solution without anything else, and you basically stop it here. So b can be any values. Right, b can be any values. And if you are going to plot this out, right, if you want to plot this out, you can plug in different b values into this equation. When you plug in a positive b value, you will get a curve looking like this. And when you plug in a negative b value, and you're going to get a flipped, basically bell curve at the bottom here. When you plug in different b's, okay, and you get a cluster of curves at the bottom for negative b. Okay, so that's a direct application of what we just did. Okay, but more frequently, you do have initial condition given. So initial condition problem. Initial condition essentially means you know what initially, right? You see here, this is your solution for output. Okay, this is a solution for output. Initial condition means you know initially what the value is for the output. So very much like, for example, let's say I have a spring, okay, and I will attach the spring with the mass, and then I will drag the spring, okay, from equilibrium to, let's say, a certain distance from equilibrium. Okay, so you hold it. So guess what? If you're trying to derive the equation of motion representing the displacement of the mass, then initially you know where it is, right? You know that's maybe 3 centimeters or some centimeters from the equilibrium location. That's what we call initial condition. Okay? Yeah. So in this particular case, for first order one, let's say if I have x equal to a is the initial condition, then suppose that I know what initial condition is. Okay? So this is an example of initial condition. And sometimes we also call it initial value. So this B at here is called initial value. IV. Okay. And this is IC. So differential equation, and you see that quite a lot. And then more precisely, you have x equal to a. Essentially, you can consider x starts at a. If this is a t variable, you can think, oh, time starts at this moment, right? This variable a starts at a at here. Okay? Yeah. Now, when we deal with this initial value problem or initial condition problem, the general solution, so this general solution, okay, should be modified slightly to cover the situation that we just talked about. Okay? The general solution for first order DE, a linear. Okay? So this linear first order DE becomes this expression. So y equal to b and then e to the power of negative, right? This is a p of x dx. So instead of an indefinite integral sign at here, this is going to be x star from a. Okay, this is x star from a. End up with x. Okay, end up with x. So your immediate reaction, okay, I got so many x's here, doesn't look right, right? So instead of writing this as x now, we will write this as a dummy variable. Let's say any dummy variable. You can use a u or tau, anything else. Okay. So this way you have a general solution, okay, giving an initial condition x equal to x start at a. Okay. Now, why this one works is you can take a look, and we can take a look at this one here. Okay, for example, if x starts at a, okay, if x start at a, then what does that mean? You will plug in x equal to a at here, right? X to a. Okay. So your y you're looking for is what's the y value when x equal to a. And a to a. Okay, yeah. And this term, whenever you have integration limits the same, it should equal to 0. So that basically gives you a b at here. And we know the initial condition when initially at x equal to a, y equal to b. So the capital B value here will be your initial value given by initial value small b. Okay. Okay? Yeah. So basically, if I deal with initial value problem, this is actually more common. Okay? you will actually make use of this particular equation now to solve for initial value problem. So let me show you one more example here. Let's say I have RC circuits. So in this RC circuit, there is no external voltage input. So the only thing it could be is the initial capacitor has certain charge around it, and the charge will start to discharge and until it fully discharges. So the equation of motion describing this RC circuit, I think we did a little bit of derivation in the previous lecture. That would be dV over dt 1 over RC times Vc equal to 0. Okay? Yeah. So this is the first order differential equation representing this system, and it's homogeneous. It's completely depends on the initial value of the response. Solving this one, you can use the separating variable technique, and you can try yourself. You get Vc of t equal to A times e to the power -1 over RC times t. Okay, so if you solve it, you get a solution like this. Okay, essentially you can plug in into the solution, you can solve it. Now, assume we have initial value, which is a voltage V0 across the capacitor. Okay. Then this is at basically t equal to 0, right? This is 0 here means at t equal to 0. Now we can substitute the initial value into the solution at here. Once you substitute t equal to 0, this becomes 1. You get A, and then the A value will be the same as initial voltage V0. So your general solution, right, will become a specific solution now. It becomes V0 e to the power 1 over RC, and then times t. Okay, times t. Okay, that's a typical procedure. This is actually a very interesting thing, small one, but it conveys a lot of concepts. Now, if you plot it out, you basically will get an exponentially decay function, right? Initial value is V0. As t goes to infinite, it goes to infinitely close to 0. Okay. So this RC at here, and you can define it, okay, as a tau, which we call that time constant. Okay, time constant. So what is time constant? So time constant is the amount of the time that it takes for this to drop to 63% of the final value. So if your final value is 0 at here, then 63%, let's say somewhere over here, and this is RC, the corresponding t value. Okay. Yes. That's just the definition. Yeah. Yeah. In the system response, will sometimes be, let's say I put in a unit step input, and you might see a response actually goes up and then settles down at a constant value. So in that case, you also have a time constant, tau at here, but this will be 63% of the upper level steady state. Okay, yeah. Trust me, this is something you will see, especially if you study control system. Okay. Okay, so that is all about homogeneous case. And a couple of minutes, let me just start this, and then we can call it a day. So non-homogeneous case. And this is the case when you have a format like this. So y prime plus pxy plus qx. Right? So this side it's a non-zero term. Okay. How do we solve it? I think I'll leave it. I'll solve it next time. We use the integrating factor method. I'll use a couple minutes to say a few things about midterm. Okay. First of all, you have a quiz next week. Okay, it's just a practice quiz on convolution and LTI system. What impulse response is? How do you get a system output when you have the impulse response and another input? Okay, so convolution combined with LTI property. So do that. It will be part of the midterm. And in terms of the midterm coverage, I haven't finalized. I need to talk to the instructor. Most probably, it will be until this case, until the next lecture. Okay? Yeah. So the first order differentiation of this. And in terms of the seating, okay, I booked 2 rooms. This room and the APSC 140. Now I have more students in this room, in this section than the other section. So we probably will actually try to evenly distribute the student into the 2 rooms. So we'll give you a list of student numbers with your names, your student numbers for each room. So look carefully and see which room that you're supposed to go. Okay, so we'll send it out later. Okay.